Hai, Assalamualaikum dan salam sejahtera. Welcome to another edition of the Physics Unmasked video series. We will be studying about object that floats. Objek yang terapung. In this Physics Unmasked video series, we will find out why some objects float in fluid or liquid like water, while some simply sink to the bottom. Kenapa ada objek yang boleh timbul dalam sesuatu cecair seperti air, manakala ada juga objek yang terus tenggelam. Now, if you try to throw a pebble and a twig into a pond, you will notice obviously that the pebble sinks and the twig floats. Similarly, if you try to push a ball downward into the water, and if you lose grip on the ball will quickly rise up to the surface and float. In other words, it is difficult to push a ball under water. And in another situation, a heavy stone feels lighter in water than in air. Okay, let's unmask the physics behind those observations. To understand the underlying physics, we shall begin by doing experiments on objects immersed in fluid or liquid such as water. Some question that we may ask: will the object sink to the bottom, float to the surface, or stay stationary? So in this simulated experiment, we will use a solid block cubes immersed under a fluid and observe how these objects behave. You may pause the video and backstep if you need to review the simulation again. Okay, so what we have here is a buoyancy simulation application program. So what you can see in the window here is actually a tank filled with a fluid, and the density of the fluid is set over here, which is currently set at 1 gram per centimeter cube. Okay, this is water, and right in the middle you can see there is an object, a cube-shaped object, and this object density can be set over here. Currently it is set at 0.75 gram per centimeter cube. So probably this is about the density of a piece of wood. Okay, on the right here shows the forces acting on the immersed object. Of course, you have the weight mg, which is directed downward, and you have this force or lifting force called buoyant force, which acts on the object upward. And down here are some numbers corresponding to the volume of the object itself. Okay, 1000 centimeter cube, and it has the mass of 0.75 kilogram, and the value of buoyant force, which is directed upward, is 9.8 Newton, and the weight of the object is 7.35 Newton. And the normal force is 0 because the object is actually right in the middle of the tank. And take note that the buoyant force magnitude 9.8 Newton is larger than the magnitude of the weight. So we would expect that when we start the simulation, this object will rise up and float on the surface. Okay, let's begin the simulation. Right, clearly you can see that the object floats on the surface of the water, and you can see that 75% of its volume is submerged below the water, and only 25% of its volume is above water surface. And whilst floating, there is no net force on the floating object. So as you can see here, the buoyant force is directed upward, has the same magnitude as the weight which is directed downward. And even you can see down here, the calculation indicate that buoyant force is 7.35 Newton and the weight of the object is 7.35 Newton as well. So the two forces have the same magnitude but oppositely directed. So the object is floating stationary. So next we will change the density of the object to that of ice. Okay, ice has a density of 0.917 gram per centimeter cube. Okay, so we reset that. Okay, we have set already the density of the object is 0.17 or 0.92 gram per centimeter cube. This is actually the density of an ice cube. And again, we have the same information about the buoyant force, 9.8 Newton, and the object weight now is 8.99 Newton. Okay, then again you can see that the buoyant force is greater than the weight. So we would expect this ice cube, which is right in the middle of the tank, will actually float onto the surface. Okay, let's run the simulation. Right, that's interesting. So now the ice cube is actually floating on the surface of water, except now that more of the volume of this object is submerged underwater. 92% of the ice cube's volume is below the surface of water, and only 8% of the ice cube volume is above the water. So again, since the ice cube is floating stationary, the net force will be zero because the buoyant force and the object weight has equal magnitude but opposite direction. Okay, next we will change to another object which has a larger density. Okay, so 1.8 gram per centimeter cube. So this is like a piece of brick. All right, so we put it in the middle of the tank, and the brick now has a density of 1.8 gram per centimeter cube, and we run the simulation and see what happened, whether the brick sink or float. But that can be expected because the brick will sink. Is expected because, as you can see, buoyant force 9.8 Newton, which acts upward, is less than the object weight, which is 17.64 Newton, which acts downward. So anyway, let's run the simulation. Yes, so an object which has a density of 1.8, which is greater than the density of water, which is 1 gram per centimeter cube, result in the object sinking to the bottom of the tank. So while at the bottom of the tank, there is a normal force 7.84. That one is from the base of the tank, right? And the object weight is still 17.64, and the buoyant force is 9.8. Okay, so actually the object remains at the bottom of the tank. Having seen the simulation, we will now analyze what happened to an immersed object under the action of pressure by the liquid and the forces acting on the object surfaces. If you have seen the simulation carefully, you may be able to draw some conclusions as to the relationship between the density and the tendency for an object to float. Okay, now let's see how the analysis goes. Beginning with the analysis of objects that are fully immersed in a fluid. Okay, let's have a solid object in the shape of a cube of dimension d. Okay, so the object is immersed in a fluid or liquid like water. So the object is subjected to pressure by the water, and this pressure acts on the whole surface of the object. So one thing to note here is that the pressure acting on the side around the block actually cancel each other, because opposite side of the points on the same depth have the same pressure magnitude. Okay, so but the pressure on the top surface is less than the pressure on the bottom. Okay, so then we indicate that the pressure at the top is by Pt and the pressure at the bottom by Pb. And we recall that from the definition of pressure is equal to force divided by area, and pressure also in a liquid is given as the density, gravity, and the depth below the liquid. And so that we can define the force that acts on the top surface as Ft is equal to the pressure top multiplied by the surface area of the top surface, and similarly the force from the bottom or onto the bottom surface, Fb, is the pressure multiplied by the area. And if we define the depth of the top surface below the water surface is h1, while the depth of the bottom surface as h2, so we can now write the force on the top surface as rho g h1a, and on the bottom surface as rho g h2a. Okay, then since pressure from the bottom is greater than pressure at the top, it follows that force on the surface or on the bottom surface has to be greater than force on the top surface. So we can now write the net force which is acting upward, so F up is equal to the difference between the bottom force and force from the top. Okay, so this will be equal to rho g h2 minus h1 kurungan a, right? And this can be written as density multiplied by G multiplied by D and multiplied by the area A. Note that A is actually equal to D squared. Therefore, D multiplied by A is the volume of the immersed object, and this is equal to the volume of the liquid displaced by the object. So what we have got here is an expression saying that the upward force on the object by the liquid or fluid depends on the density of the liquid and the volume of the liquid displaced by the immersed object. And this upward force on the object by the liquid is called the buoyant force. So in general, the buoyant force is an upward force exerted by a fluid on any immersed object. Furthermore, if you look at the expression for buoyant force, where rho multiplied by g multiplied by v, that is actually the weight of the liquid displaced in that volume. And so we can claim that the magnitude of the buoyant force always equals the weight of the fluid displaced by the object. This statement is known as Archimedes' principle. Okay, is the buoyant force the only force acting on the object? No. The object has mass and therefore has a weight W, and this weight acts downward, and which is equal to mg. So there is now a net force on the object that will determine whether the object floats or sinks. Okay, so let's just say force net is equal to the buoyant force minus the weight of the object, which is equal to rho g v minus the weight of the object. So okay, so we have buoyant force term and the weight of the object. Now if buoyant force is greater than the weight, if buoyant force greater than the weight, the net forces will be positive and the object floats. If the buoyant force is less than the weight of the object, net force will be negative, and of course the object will sink. And we can also write in terms of density the expression for this net force. That is, F net is equal to the density of the liquid multiplied by G and the volume of the liquid displaced minus the density of the object G and the volume of the object that is fully immersed in the liquid. So such that we can factor out the G and the V, we get just an expression for the difference in the density between the two, between the object and the fluid. Okay, so the final expression for the net force on the immersed object is actually the difference between the difference in density between the object and the liquid multiplied by gravity and the volume of the liquid displaced. So this brings us to another simple conclusion regarding whether an immersed object will float to the surface or will it sink, based on comparing the density between liquid and the object itself. So you can say it in words like object floats if its density is less than the liquid. Alright, so this is what this expression means. Part of the simulation has also demonstrated that the characteristic of objects floating stationary in a fluid or liquid. So in this next analysis, we will concentrate on objects that are floating stationary in a liquid. Okay, we see here that both the wooden cube and the ice cube blocks float in water, and that is because due to the fact that both objects have densities less than that of water. And one obvious difference that between the two objects is that the wooden cube floats with more of its volume above the water surface compared to the floating ice cube. Okay, so we will find out an expression that describes this behavior more clearly. Recall that when, according to Archimedes' principle, the buoyant force that acts on the object is equal to the density of the liquid, G, and the volume of the liquid displaced. Yeah, regarding the usage of the buoyant force expression here, particular attention has to be given to the determination of the volume of the liquid displaced. This is because if the object is fully immersed in the liquid, the volume of the liquid displaced is equal to the volume of the object itself. However, if the object is floating, the object is only partially immersed in the liquid. That is, part of the object is still above the surface. Therefore, the volume of the liquid displaced would be smaller and only equal to the part of the volume of the object that is under the liquid. Therefore, the magnitude of buoyant force in each case will be different. In fact, the buoyant force for object that is immersed fully in the liquid will be greater than the buoyant force for an object that is floating in the liquid. Okay, so now let's just identify all the forces acting on the floating wooden cube. So the forces are, we have buoyant force BF that acts on the object that points upward, and then we have the weight of the block that points downward. Since the object is floating stationary, the net force on the object is 0. So meaning to say that the buoyant force minus the weight has to be equal to 0. In other words, the buoyant force will be equal to the weight of the object. Okay, remember that the weight of the object can also be written in terms of its volume, that is by multiplying the density of the object with G and the volume of the object, or of the wooden block. So we can rewrite this equation in the form of rho G and volume of the displaced liquid equal to the weight, which is now in terms of the density, gravity, and the volume of the block itself. Solving for the volume of liquid displaced, we get volume of the displaced liquid equal the ratio of the densities object and liquid multiplied by the volume of the solid cube block. And if you look at the figure, the volume of liquid displaced is actually also equal to the part of the volume of the wooden cube, or part of the volume of the object that is immersed under the liquid. So we can also say that Vd is actually equal to the volume of the object below the surface of the liquid. Okay, then with the expression that we have here, we are now in position to actually, at least in terms of percentage, determine how much or how many percent of the block or the object is exposed above water and how much is submerged below water. Okay, so let's try use the data for density wooden cube and the density of ice cube. Okay, for the wooden cube object, the volume under liquid would be okay, Vd is equal to the ratio of the density of wood divided by the density of water multiplied by the volume of the wooden cube itself. So from here we can see that the fraction of the volume under the liquid is 0.75. That amounts to about 75%. Okay, 75% of the volume of the wooden cube is under the liquid. For ice cube object, Vd is equal to 917 over 1000 multiplied by the volume of ice as a whole. That turns out to be 0.917 by fraction, or about 92% under the liquid. 92% of the ice cube is under the liquid. So going back to the figure, here is 75% below water, the volume of the cube, and only 25% of the wooden cube is exposed above the water surface. Whereas for the ice cube, 92% is below water and only 8% is exposed above water. Okay, so what can we conclude from this analysis? Well, okay, based on the expression that we have derived, it can be now claimed that the volume of the object under the liquid depends on the product of the ratio of the density of the object with the liquid multiplied by the volume of the object itself. So, in conclusion, for a freely floating object, the volume of the object that is below the liquid depends on the ratio of the density of the object and the liquid multiplied by the object real volume. The analysis that you have seen have considered two cases of object in a liquid. One situation is when the object is fully immersed in the liquid, The other case is when the object is floating on the surface of the liquid. So with that analysis, we have come to the end of this video series. Let us summarize some of the key concepts that we need to understand and remember in order to explain and appreciate why objects float or sink. Buoyant force depends on the density and volume of the displaced fluid. Objects float when its density is less than the fluid density. When object is freely floating, the buoyant force is equal to its weight.